Welcome to Cortex Central, the podcast where we explore the latest developments and trends in mathematics and science. I'm your host, Rahul Kuntal, and today we're going to talk about algebraic geometry and some of the recent big advances in this fascinating field. Algebraic geometry is the study of geometric objects that are defined by polynomial equations. For example, a circle is an algebraic curve because it can be described by the equation x squared plus y squared equal to 1. Algebraic geometry has many connections and applications to other areas of mathematics, such as number theory, topology, complex analysis, and representation theory. One of the main goals of algebraic geometry is to classify and understand the properties of algebraic varieties, which are the sets of solutions of systems of polynomial equations. For instance, how many solutions are there? How are they distributed? What kind of singularities or symmetries do they have? How can we compute with them efficiently? To answer these questions, algebraic geometers have developed many powerful tools and techniques, such as sheaf theory, cohomology, schemes, stacks, moduli spaces, and derived categories. These concepts allow us to encode and manipulate algebraic information in a more abstract and flexible way, and to relate different varieties through various functors and correspondences. However, some of these tools also have their limitations and drawbacks. For example, schemes are very general objects that can handle singularities and infinitesimal deformations, but they are also very complicated and hard to work with. Moreover, some geometric phenomena, such as analytic continuation, transcendental functions, and non-Archimedean fields, are not well captured by schemes. This is where some of the recent advances in algebraic geometry come in. Two of the most prominent figures in this area are Peter Scholz and Dustin Clausen, who have introduced and developed new theories that aim to overcome some of the difficulties and challenges of classical algebraic geometry. One of these theories is called perfectoid geometry, which was initiated by Scholz in his PhD thesis. Perfectoid geometry is a way of studying varieties over non-Archimedean fields, such as the p-adic numbers, by using a special class of rings called perfectoid rings. These rings have a very nice property. They are almost perfect, meaning that every element has a unique pth root, where p is a fixed prime number. This property allows us to simplify and reduce many problems in arithmetic geometry and number theory, such as the Langlands program, the weight monodromy conjecture, and the Riemann hypothesis for curves over finite fields. Another theory is called condensed mathematics, which was developed by Clausen and Scholz in a series of papers. Condensed mathematics is a new approach to analytic geometry, which combines algebra and topology in a novel way. The idea is to replace the usual notion of topological spaces by a more general notion of condensed sets, which are sets equipped with a Grothendieck topology. A Grothendieck topology is a way of specifying which subsets of a set are considered to be open and how to glue them together. This allows us to deal with more exotic and irregular spaces, such as profinite sets, spectra of non-commutative rings, and tail spaces. Condensed mathematics also provides a new framework for defining and studying analytic rings and spaces, which are rings and spaces that are locally given by power series. For example, the complex numbers are an analytic ring, and the complex plane is an analytic space. Condensed mathematics allows us to generalize and unify the classical notions of complex analytic spaces, rigid analytic spaces, and adic spaces, and to relate them to each other through various functors and equivalences. Condensed mathematics has many applications and implications for algebraic geometry and beyond. For instance, it can be used to study the cohomology of algebraic varieties, the homotopy theory of schemes, the derived algebraic geometry of Lurie, and the motivic homotopy theory of Voevodsky. It can also be used to construct new invariants and structures, such as the cyclotomic trace, the Witt vectors, and the prismatic cohomology. These are just some of the highlights of the recent advances in algebraic geometry and the work of Scholz and Clausen. Of course, there is much more to say and explore, and many open problems and challenges remain. Algebraic geometry is a rich and vibrant field, with many connections and interactions with other fields of mathematics and science. If you want to learn more about this topic, I recommend you to check out the references and links that I have provided at the end of this podcast. Thank you for listening, and I hope you enjoyed this episode of Cortex Central.